Any questions before we get started? Residents? Aspect? Diels-Alder reactions?
On the Diels-Alder reactions, you said that some of those can rotate, and I was curious how they rotate when they're pi bonds. Like where you have like a trans, and you have two pi bonds, and then there's just this isn't here, but there are these pi bonds here. And
S-cis versus S-trans?
yes.
This would be S-cis,
Right.
and this would be S-trans.
Right. And you said they can rotate.
Questions again?
How do they rotate with those pi bonds?
Keep asking. Single bond here can
Right.
rotate.
But it's attached to pi bonds, so that's why I was confused.
What do you mean it's attached to pi bond?
Where is it rotating at? Because it has to rotate about those ends where those pi bonds are, right?
Did you build a model?
I didn't yet, no.
I've got extra things here like an H. Can you see that at all?
Yeah.
Double bond here, double bond here.
Okay. All right, I just was
The
looking.
two carbons are the bond connecting these two carbons is spinning.
Okay.
Not these two. See, these two, that's the pi bond. You can't rotate the pi bond. And the
But
two
the-
H's, you can't rotate that. But how about that bond there?
Okay.
And so S-trans, S-cis.
Got it.
But there's a question in there if you want to ask it.
I don't think that I have it.
Anybody have the question?
The p orbitals for the 2-3 carbon interact with each other to prevent the rotation.
Do you think that this p orbital is interacting with that p orbital? Yes, that's called resonance and conjugation. And thus, your question
Would that prevent or make it less likely for the
is,
bond to rotate?
is the pi bonding that you would need to be able to see there, does it restrict the rotation? There's the good question. And I alluded to that in my video. What did I say?
You said
I probably just said it's a good question.
Yeah.
Okay. Does the conjugation between this p orbital and that p orbital restrict the rotation? Well, since these are known to be able to convert from S-cis to S-trans, apparently not. And that gets into, well, why not? Are they overlapping? And this gets into a can of worms. And, okay, so maybe the rotation is much slower than a standard single bond rotation. You would have to look into what's known about that question. Okay, that's the question. I thought. So, which form does have to be in to do Diels-Alder or S-cis? Because these two are going to react this way with an alkene. If I'm going to make the two bonds to you right here, I can't do it like this. You're going to be like, hey, your other hand is on the wrong side, right? Now I can react, S-cis. Right? So, and there are some compounds that they're stuck like this, and then they can't do Diels-Alder. And there's an example where, okay, they can be stuck in the S-trans form. There's also, some are stuck in this form, and those that are stuck in the S-cis form actually react to Diels-Alders faster, because they're always ready to react. Otherwise, it's maybe an equilibrium back and forth, and that actually may be the preferred equilibrium. I don't know. You could argue maybe. So yes. Resonance. Questions about resonance?
On the pink sheet, I'm sure I'm having a lapse. Anyways, can you draw a Lewis structure for a nitrogen attached to two oxygens.
We did that at the end of class on Monday, didn't we? Nitro group? Nitro group. Nitrogen, double bond to one oxygen, single bond to the other. This is a minus, the nitrogen is positive. That's a nitro group. You'll see it in organic 2. You will make a nitro, if you have me, you will make a nitro compound in lab. What was the question about that? Located here.
Never mind. It was. I'm good.
Question.
No, I'm good now. Thank you.
I mean, it's, don't let charge throw you. There's charge there, but it's structure. You have something here, electrons in, electrons out. But you can also do resonance. Can you draw resonance of a nitro group? Yeah, these electrons here, these electrons here, and you get a resonance structure that looks like what? Double bond now here, single bond now here. That oxygen is now minus, right? Nitrogen still plus, yeah? Resonance structure of nitro group, if I agree. Yeah, what's the true structure? Neither of those are now fake. True structure of the nitro group is, which nitrogen-oxygen bond is longer?
Same way.
Yes, they are the same. If you could actually see a nitro group, it's very symmetrical. It would look like that. That's how it actually, if you could take a electron microscopic picture of it, that's how a nitro group actually looks. Again, we like to draw big structures. We don't like to draw these partial lines.
Well, what would the nitrogen? In your notes, you say that nitrogen might have an exception to the octet rule. What would that be?
Where did I say that?
Golden rule number 4, second line. But maybe we're not exposed to that. Because I was trying to draw it.
Somewhere. I told you that before. There's exceptions to everything.
Okay.
I mean, you can have. You remember carbines formed during the synthesis of cyclopropanes. Alkene can react with carbene. You can also have something called a nitrene. Nitrene, E and E. The nitrogen would not have an octet. Nitrenes are sometimes seen, but it's only one further away from carbon. Carbon we see without an octet all the time. Carbocations, no octet. Does that mean there's a big divide and nitrogen is absolutely no? You can sometimes see a nitrogen with no octet, but I would consider that an exception. And don't do it unless we have a great reason to do it. Oxygen, no octet. Now we're getting even further more electronegative. And I would actually say, I don't think I've ever seen an oxygen with no octet. Any structure that is known to have reality. But I have seen nitrogen. But I would just keep it general. Anything to the right of carbon, make sure it's got octet. But you've heard there are exceptions, right?
Yes, sir.
I just happened to mention there because I'm thinking nitrene when I write this. So I don't want to completely lie to you. Okay, nitro group. The nitro group you can do resonance into. If you have something over here, you can move electrons this way, and that's what you need to be practicing on. It's a good thing to practice. You'll see it in organic 2. This is a prereq to organic 2. We'll make sure you succeed in organic 2 when you get there. Okay, I need to send out the answer key to some of these in the resonance handout. Let's see how we can finish this up. Good question here. Which is more stable? Which of these three carbanions is more stable? Which one's least stable?
The left.
Least stable. Not conjugated. There's no resonance here. There's no resonance delocalization of this anion. Do not draw a resonance structure. The carbon is holding the entire minus charge. Can you do resonance here? Yes. Electrons in, electrons out. Resonance arrow, and we can get double bond here, and now carbanion over there. What's the true structure? It's a blend between the two. The charge is spread over two different carbons. Yeah? Resonance delocalization of charge is better than none. How about over here? Same thing. Great place to begin with resonance if you have a conjugated lone pair, electrons in, electrons out. And we get double bond here. Get to that. Okay, which carbanion is more stable? This one or that one? That one. Why? Because the charge here is spread over carbon and carbon, the minus charge. Over there it's spread over what?
Carbon.
Carbon and oxygen. Oxygen is more electronegative. It can handle minus charge better. Okay, so they're both resonance delocalized, but in this case, one resonance is better than the other. You have a difference in atom electronegativity. Over here, these are equal contributors. What about over here? Are these equal or is one better than the other? Yeah, this is major. This is minor contributor. So in the blend over here, is there more minus on oxygen or carbon? Oxygen. That makes sense. And this is all the same idea of electronegativity. Electrons are going to move more toward the oxygen. Like water in a garden hose would move more downhill, or gravity, electronegativity. It's physics, right? Because oxygen has more protons in the nucleus. Protons are going to attract the electrons more. You understand where electronegativity comes from? Question?
So if you were to draw the structure with a blending of the bonds, would you put a partial negative on the oxygen and the partial positive on the carbon? Or
No. When is there ever positive on carbon?
there isn't. But we said that like the oxygen would be more likely to have the electrons like compared to carbon.
Yeah, but that doesn't mean carbon's positive. Carbon
Right.
just got its less minus than the oxygen.
So we can't really draw the blended diagram.
No, you can. You can always draw a hybrid. It's just not a perfect blend. It's a bond. I mean, it's not exactly a bond and a half because of these equal contributors. No. Is the bonding between the O and the C here more closer to double or single?
Closer to double. Closer to single. Oh, it should be.
Closer to single.
Yeah.
Here's major. Major means the kid looks more like that one. There's more single bond character here. But how do I differentiate? Again, I told you, we're just going to say bond and a half. But understand it's not a perfect blend. That's also a bond and a half. How much charge is here? Partial minus, partial minus. That's as if it was a perfect blend. But we know it's not. There's actually more minus on which atom?
Oxygen.
Oxygen. All this comes from knowing that's the major one and then saying, hey, that contributes more to the blend. There's more minus on oxygen. There's more single bond character here. There's more double bond character here. But how do you want to show that? There's no simple way of showing it other than saying, describing it. Now, if we had some colors, we could have maybe light blue versus dark blue or something. But we're not going to get into 1.3 bond, and it gets a little. Okay, so resonance, it's the same number of resonance structures, two total, or one additional from the beginning, But resonance allowing us to put the charge on oxygen, very good. Very stabilizing effect. So the charge is delocalized. This is pi bonding. This is resonance. This is where, it's the same old discussion, but it's, hopefully you're kind of getting there. Okay, I'll let you do these on your own. You'll be able to draw resonance structures, venting rings, here, acid base. Those acid base stuff, you can look back. Hand out for week 1, but again, I'll also send out an answer key. You can check yourself there. How many pi electrons are in the extended conjugated systems coming down below? Anybody got an answer? Anybody got an answer there?
Eight.
Not 8.
12.
Anybody? Not 12.
14.
Not 14.
All right, let's try the next one. Please look at that. You need to understand the structure up there. Pi, you can draw your pi system. The compound below in the box is known to exist in equilibrium with a major tautomer. Which OH tautomer shown below is most stable and thus the major tautomer? Both of these are tautomers of that one over there. Everybody agree? Both of these are enol tautomers of the one in the box. Yeah? Which one is more stable and thus going to be the major one at equilibrium?
The one on the left.
Why the one on the left?
Because there's more electrons participating in the conjugated system.
Yeah, there's more conjugation. Didn't we say conjugation is better than none? That's where we began the handout where we talked about heat of hydrogenation, diene, conjugated diene versus non-conjugated diene. Essentially, the one on the left is a conjugated diene, the one on the right is a non-conjugated diene. I mean, the answer should be pretty straightforward. Yeah. How many electrons in the pi system over here? That should be quick. I'm not seeing why we're not getting that quick. How many electrons in the pi system over there? You should have been able to answer that week 1 or 2. Question? How many electrons in the pi system here? Why are we not seeing that, guys?
6.
Your answer is what?
6.
The answer is 6. Why are we not seeing that? We need to draw the pi system. You got a pi bond here, everybody agree? 1, 1 pi bond. You got a pi bond here, everybody agree? 1, 1 pi bond. Okay? And one of these lone pairs is in a p orbital because anytime a lone pair is next to a pi bond, it's going to want to be in a p orbital. And you have pi system there. How many electrons in the pi system? 1, 2, 3, 4. Lone pair makes 6. The lone pair is conjugated with the 2 double bonds. It's 6 electrons. Seeing it now, should you have gotten 6? I would hope so, yes. But I'll let you get the answer up there on your own because there's, all right. Resonance is the cause of many things in organic chemistry. Hopefully you maybe see that. Lots of answers will come from resonance. Just like lots of answers come from hydrogen bonding. Okay, 2 very important things in chemistry, organic chemistry. Some enols are stable enough to exist instead of undergoing tautomerization in carbonyl form. Okay? Up here, ketone form is favored. Of these two, this one's better. The ketone form is still favored. That's what we said. Carbonyl form is favored over enols, right? But of course, there's exceptions. Here's an exception. The anticoagulant known as warfarin, we can show here carbonyl form or enol here. This is the enol, right? Enol of this. It's an equilibrium. But actually, this one is favored. Why is the enol favored here? Two reasons. One is what?
The OH and O can interact intramolecular forces, hydrogen bonding.
Imagine that. Hydrogen bonding, yes. Hold on. You're going to have to tell me what, where. What can interact?
On the right side, the rightmost carbonyl, you can rotate the sigma bond so that the carbonyl is close to the OH.
Oh, okay. So you want to have hydrogen bonding between this H and that O?
Yes.
You'd have to rotate this. Okay, you can rotate that and position this carbonyl there. It would be a what type of ring within hydrogen bonding? 1, 2, 3, 4, 5, 6, 7. It's an 8-member ring. Okay. You're asking the oxygen to come over and hydrogen bond with the H, but it's going to be an 8-member pseudo ring. Okay. That's sort of like having an arm twice as long and saying, okay, come clap. It's going to be like, it's so long. So it may be a little bit difficult to swing around and be positioned. It may be like more like this. 5 and 6 would be better, even when you're looking at making a IMF hydrogen bond. Okay. So hydrogen bonding, imagine that. Answer the last question. What's another reason that this is here? Well, another reason this structure is favored over that one. Because the double bond that we put here with our ene is conjugated with, well, it's conjugated here, but it's also conjugated here. It's also conjugated here. You got all this extended conjugation now. Over here, there's no p orbital here. Okay? Over here, this is sp3, and you don't have as much conjugation. You have this extended conjugation now. And if it's conjugated here, it's kind of cross-conjugated, but if you just look here, lone pair, double bond, double bond. That's 6 pi electrons. Over here, if you ignore this, and you ignore that, you have 2 different pi systems, 2 and 2, and they're not conjugated to each other. But over here, everything is conjugated, and instead of 2 and 2, it's now 2, 2 and 2, 6. Extended conjugation. That's a good thing. And warfarin is typically drawn as the structure on the left, and if you run things like IR, if you run an IR warfarin, you'll actually see an OH group in the IR, telling you that, hey, the enol must be in predominant form here, and I'm seeing evidence of it. And if you run NMR, which runs organic 2, you'll see that it is like that structure. You'll see evidence of that structure. And so if you think this is a structure, but you see an OH in the IR, you've got problems. There's no OH in that. There's no OH in that structure. Okay. So there's an example of how resonance or hydrogen bonding, there's 2 answers there, could make an enol form favored. And why it would be an exception. Okay. All right, need to push through resonance there. I'll look for the email with the answer key. Chemistry of Dienes. One more page. What we'll see is, okay, we got a diene here. What we're going to see here is something interesting. We can do a reaction good old classical reaction, hyperhalogenation of HBr. I do a pi bond. But it turns out you can get different products depending on if your reaction is in cold or hot. Different products. Why? What's going on here? And what is the mechanistic rationale for this? All right. Then we'll do Diels-Alder, but of course that's by the video, and doing that in lab, and again lab this week continuing. And we're going to do TLC of our product. If anybody's interested in maybe doing a reaction with the product, you can stop by and I can maybe propose something. Again, a reaction that is covered in organic 2. But the product is in anhydride, as I mentioned in the pre-lab. But you can do chemistry of anhydride. You want to give that a try. One reaction you can do. I mean, there's many reactions to do. But we can give one a try if anybody's interested. So, Diels-Alder. Anybody give a quick answer to that one? Which compound looks like it can be made using a Diels-Alder reaction?
Tamiflu,
Tamiflu 1.
because there's a cyclohexane.
As you see, a cyclohexane, Diels-Alder, the basic Diels-Alder which we're covering gives a cyclohexane. And actually in one of the handouts, maybe even in mass, no, I'm not sure which one, it's actually going to be 2. There'll be a future one that includes the Tamiflu synthesis, but you already got one. It showed the first step is a Diels-Alder. Yeah. Is equimate above a conjugated diene or non-conjugated diene? Got 2 enes, so is a diene, is it conjugated or not? Don't answer that. Too easy, right? Everybody good? Right? Clearly not, right? Okay, good. What do we have down here? Amphotericin B, antifungal drug. You ever seen that in biology classes? No? How many alkenes are conjugated? 1, 2, 3, 4, 5, 6, 7. 7 conjugated. What do you want to call this type of compound? Diene? Triene? A lot of times when you just get a lot, it's called a polyene. Okay? You get up 5, 6, 7, or 10, or 11. Beta carotene has, I think, 11 double bonds conjugated. And it's called a polyene. Okay? Multiple E. Right? Polyenes. Amphotericin B is called a polyene. What type of compound is it? The first thing you might say, well, it's a polyene. What other functional groups do you see? Lots of OH groups. I see a carboxyl group, amino group. I see a huge ring that consists of maybe about 20 or 25 atoms. See the big ring there? Okay. That's actually 2 other rings, 2 other 6-member rings. Yep. Okay. Structure and organic chemistry, right? Chemistry of dienes. We've already covered A. B, nomenclature. Longest continuous carbon chain. 1, 2, 3, 4, 5, 6, 7. 7 is what? Is that a heptane? But this ain't just heptane. If there was only one double bond, we could call it heptene. Since there's 2, what do we do? Instead of ane or ene, it's heptadiene. Pretty creative. It's called heptadiene. And if there were 3 alkenes in the heptane or whatever, what would you call them? Heptatriene, yes. Okay, but we're just going to name diene. Okay, heptadiene. But you got to indicate where the double bonds are at, because it may be double bond here and here, or here and here. You indicate double bond just by the first number, just like with alkene. So what do we want to put in front of this? What's the 1 in? Left or right? Right. All right, 1, 2. Right? 2, 4 heptadiene. This is the position of each alkene, the two alkenes. One is at the 2 position, that is 2, 3. And the other one is at the 4, 5, but we just say first number, right? So it's just twice the fun of an alkene nomenclature. 2, 4 heptadiene. That's pretty straightforward. Well, if that's that, what is this? That's also 2, 4 heptadiene. But it's a different compound, isn't it? How are we going to distinguish them?
Easy.
What's the relationship between these two? They're stereoisomers, okay? And they're only distinguished by some stereochemical descriptor. What do we need to put in front of this to clarify this name?
E.
Both of these alkenes are trans, but in terms of more specific E and Z, they're both what?
E.
E. We can put over here E, comma E, to clarify the geometry of these alkenes. Over here, this is the same name. What do you want to put in front of it? What is this one here?
Z.
That one's Z, and this one is E. Over here, you would say Z, comma E, dash 2, 4 heptadiene. And the Z goes with the 2, first number, and the E goes with the 4, the next number. You may see somebody say 2Z and 4E, but really not needed. You can just do it like this, first number goes with that. Okay, name the compound on the far right. Somebody got a name?
EZ15 oxidine.
Tell me again, Favor.
I don't think it's chlorine either.
Name?
EZ15 chlorine, octadiene, chlorooctadiene.
Octadiene?
State, right?
Not octadiene. You gotta, there's something you gotta remember about, I think we'll mention in just a second. It's not octave. What is the parent chain here? Hex. Hexadiene. Name here, E. 1 chloro. 2 propyl. 1, 5 hexa. Diene. Anybody have something else? Longest continuous chain. 1, 2, 3, 4, 5, 6. Why not 1, 2, 3, 4, 5, 6, 7, 8? Because just like with alkenes, the double bond or the double bonds all need to be within the longest continuous chain. And so, Faber, as you go here, that carbon of this alkene is not in the longest continuous chain. Okay? All carbons of all your alkenes have to be in the longest continuous chain. So 1, 2, 3, 4, 5, 6. That's the longest continuous chain that contains all carbons of all alkenes. So that's where that's a hexadiene we just circled. What's the one in, the left or right?
Right.
Either way you go, this would be, alkenes would be at 1. But this one you would also have a substituent at 1. So let's make that 1, 2, 3, 4, 5, 6. So it's at 1, 5, hexadiene. What are the substituents? Well, chlorine's on the 1, we got that. And on the 2, there's a what? Propyl. So I'm liking the name. And the stereogenic alkene is E. E obviously refers to this one, because that one's not stereogenic, and it has no E or Z. You only need one. And it is E because over here, high priority group on this carbon, H or chlorine, chlorine. Over here, carbon or carbon. Oh, this was good. Okay, we got to make carbon or carbon. Same. Same. Not the same. This carbon has just H's, this carbon has another carbon. Actually has 2 other carbons. So it would be that, and their opposite, that's E, right? I like the name, good. Anybody have a question? So pretty straightforward. Alkene has to be in the longest continuous chain. Same thing as if it was just a regular monoalkene. Okay, terpenes, terpenoids, these are natural products, a class of natural products. We saw a class before, alkaloids. What's an alkaloid? Natural product that contains a basic nitrogen, like morphine, okay? Nicotine, all right? Lots of them, lots of beautiful molecules. What? You don't like them? No? Comment on terpenes. Okay. Terpenes are, well, these are all terpenes. Well, you're not going to find the basic nitrogen, because if you did, it would be called an alkaloid. A terpene is a compound, natural product that ultimately comes from this building block, which is, guess what? A diene. And you can name this. The name would be 2-methyl-1,3-butadiene. I'm going to check your nomenclature. All right? But these can polymerize and give larger structures. And since it's just kind of multiples of this, that's C5H8. But look at limonene, which is found in lemons and other citrus fruits. It's times 2, C10H16. So this is where 2 of these came together somehow and dimerized and made limonene. Okay. You can also recognize terpenes because see this methyl coming off the chain? And so your products are going to have these methyls sort of all over the place. You see how he's got this methyl here and this kind of looks like maybe a methyl there that's kind of coming off? Yeah. It's like 2 of them because 2 of these. And so look at all these structures. See all these kind of methyl groups around? They come from this methyl group here originally. So that's common to terpenes. Now, some of them may have oxygen. Well, where did the oxygen come from? There's none in isoprene. That's called isoprene, slang name. This is where maybe after something was formed and one of the double bonds got hydrated. And we formed an alcohol. So it's not exactly a terpene, it's called a terpenoid. What does that mean, terpenoid? What's a humanoid? Kind of human-like. Okay. It's not exactly a terpene because it's not exactly a multiple of that. But it came from that and it's very similar. So it's called a terpenoid. Okay? There's beta-carotene. How many double bonds? I think that's 11 conjugated. Beta-carotene is a terpene. poly. All right? So it's a class of natural products that ultimately comes from the monomer, which is a diene called isoprene. Mother Nature uses isoprene to build some pretty sophisticated molecules. Taxol, I didn't show Taxol. Taxodiene is closer to this being. Is this an exact multiple of that? 8 times 4 is 32. Yeah, this is an exact multiple where 4 isoprene units came together and miraculously led to that molecule. Can you give a mechanism for that? That's final exam. 4 molecules of isoprene, a mechanism for forming taxodiene. All right, did you do it? One question, 100 points. You can bring any books you want. This sounds like my exam in graduate school in my second organic chemistry. That's kind of how it was. It was one question. You can bring any books you want, and it was 4 hours long. And okay. I did pretty well. And I didn't use any of those books. Because if you got to go through books and hunt for it, you're probably not going to, you got to just know it. Right? I think you guys think open book exam sounds good. No, you don't want an open book exam. You're going to spend all your time turning pages and hunting and you're run out of time. Right? Everybody agree? I don't know what the point of that is. But we were allowed to bring any resource. I mean, in some regard, if you need to check something, maybe get an idea. But you can't rely on all the books too. Okay. Sometimes I show that in organic too. Okay, let's move ahead here. 1,2 versus 1,4 additions. Chemistry. If you take this diene reacted with HBr, we can get a product. Cold temperature though. HBr, one equivalent. Okay? And say that here. Usually implied unless it says excess. We can get that product. How do we get that product? Well, we've been doing this for 6 weeks. We got H+. This alkene can react here. Where are we going to leave cation at? Left or right?
Right.
On the right, correct. Why on the right? This looks familiar? Why on the right? Oh, that's secondary? Well, it's more than that. Why on the right? Give me another reason. H resonance stabilized. Yes, that is another reason, and let's make it the more important reason now. Resonance stabilized, right? Okay. We can do resonance. Can you draw a resonance structure of this carbocation intermediate? Yes, conventional wiper over. What do we get? Double bond now there, plus here. Yeah? Resonance stabilized. What's the name for this type of carbocation next to a double bond? It's in the previous handout, resonance handout. Maybe we didn't mention it. We mentioned benzoic. Allylic, yes. Allylic. It's probably written on this page too. Right? Okay. How do we get final product shown? Br minus attacks where? Gives that. Attacks there, and that gives that product. Everybody good?
Stevens?
Yes.
Will the resonance structure on the left be the major product?
Don't say product, be the major contributor. Yeah, why?
Because the positive charge is on the secondary carbon.
Yes, secondary carbocation go to the primary. But that doesn't mean that this doesn't contribute to the sum. Charge is delocalized. Make it allylic carbocation, Br attachment. There you go, there's your product. This is just called a direct addition. We've been doing direct additions for 6 weeks now. Okay? It's also called a 1-2 addition because if you look at where the H is, the new H is there. If we call that the 1 carbon, where does the bromine end up? Next door, 1-2. That'll make more sense when we do a 1-4 and you see the difference. Question?
I know that you said that we could use any resonance structure to do mechanisms, but do you prefer us to show the resonance structure and then do the BR with the resonance structure, or just do it like the way you did it when it comes to like mechanisms on a test surface?
I'm not sure. Would you rather I had not shown the resonance? But you don't actually have to show resonance to get the product up there.
Right.
Why did I show resonance? Because it's there.
Right.
But I could have did this mechanism without showing that structure.
Yeah.
But then I would have glossed over the fact that it's a resonance stabilized cation.
Yeah.
Let's move ahead. Some of these questions will become more clear when we do down below. Why didn't I react with that alkene over there?
Use the same product.
I could have. I could have did the same chemistry over there, and the product would have been that there. I could have added HBr over here. Where would you make cation over here? Right or left?
Left.
Left. Bromide attached there. But that is the same product as I got shown up there, just turned around. Okay? It's a symmetrical diene. The two alkenes are identical. Okay, so it does not matter. All right? Now, of course, that's a chiral carbon, and you're going to get a racemic mixture. But that's stereochemistry, yeah? Okay. Look down here. If you take the same starting material and HBr, but higher temperature, like above 40 degrees, you're going to get this product. How do you get that product? Well, it's the same starting point. It's the same start. You get the same intermediate. How do we get this, though? Instead, the Br minus attacks there. It attacks there, you get that product down there. Now, this is called a 1,4 addition, or 1,4 product. Where's the new H down here? There. There's only 2 here. There's now 3 here. If you do mechanism, you start by adding an H here. If that's 1, where did the bromine end up? Not 2, not 3, but what? It ended up at the 4. That's called a 1,4 addition. This is indicating the positions where things were added. It's not nomenclature. It's positioning of. Okay? 1,4 addition. Kinetic versus thermodynamic. We'll clarify that. Okay. Back up here. How many intermediates in this 1,2 addition? How many intermediates there? 1. Yeah, that's 1 intermediate, right? Here's the difference, guys, and we'll finish up here. Those are fake. The true structure that's formed up there is what? This is your common intermediate for both reactions. Both cases, that's what's formed first. The only difference is, if you keep it cold, the Br minus attacks here. If you warm it up, the Br minus ends up bonded over there. Okay? Why? we'll have to pick this up next time, but it's below. Of course, you've got your textbook for reading. It's described down there, and we also have reaction coordinate diagrams here that are going to have to explain why. I've actually gave you the same reaction coordinate diagram in the reaction coordinate diagram handout from 6 weeks ago. I told you I'd give it to you later again. Well, again is now. Okay? So you already got that. No charge for giving it to you again. Okay? Please look at this terminology here. But then we need to look at mass spec, and we'll be moving on to substitution reactions. There will be a handout there. See some of you in lab tomorrow.